Hi, good morning. So how many of you have attended one of the intro tutorials for OpenFlow? Yesterday? Yeah, I mean in general, in your life. Okay, so everyone? Yes, you can raise your hand so that I can know. Okay, I was planning not to do an OpenFlow introduction, that's why I'm asking. So is there anyone that doesn't know what OpenFlow is, how it works? No? You're all good? Perfect. Okay. Okay, so, okay, this thing really doesn't want to. Okay, so have everyone downloaded this key? So download, this is a private key, and you should change the permission to 600 like you did in the first day tutorial. And the passphrase for this key is GEC19, no lowercase, one word. Okay? When you're going to need it. Okay, so today we're going to do an OpenFlow experiment, and we're going to instrumentize and monitoring using LabWiki. How many of you have used LabWiki or taken the LabWiki tutorial? Everyone, perfect. Good, okay. So let's, okay, so I'm going to talk very briefly about OpenFlow, then we're going to talk very briefly about the LabWiki, and then Divya will do a demo of the whole tutorial, and then we'll let you have at it. Okay, so OpenFlow experiments. I don't know how many of you have used OpenFlow outside a tutorial setting, so like try to use it by yourself. But it's OpenFlow experiments are very hard to debug, especially when you have to deal with real hardware, right? Because it's there is a lot of network configuration. If you want to debug something remotely, then you need to coordinate with the admins. For example, if you're having problems, if your packets do not go through and you're using, like a hardware switch in the other side of the country, you actually need to get the admin in order to be able to get traces, to see what's happening, get flow tables on the switch. You don't have access to these things when you're using hardware switches. You have many, many different network elements in play. You have especially if you're using the hardware switches in Genie, there are other non-OpenFlow elements in the middle that might interfere with your forwarding. And you don't have access to the switch. You cannot just log into the switch and see what's happening, okay? So always, and whether you're using Genie to deploy your OpenFlow experiment or you have your own test bed with your own OpenFlow switches in the lab, it's always a good idea to start testing and writing your controller in using a more controlled environment. So out there is, for example, Mininet, which is a full system that you can bring hosts and software switches and everything to test your experiment. The only one problem with Mininet is depending on the application you want to develop on top of it, how much access you have to the host, because the hosts are like virtual machines on one virtual machine, so it's like they're not very powerful hosts. And the other is to use, for example, Genie or other virtualized technologies where you can bring up your hosts as real VMs and use the OVS image in order to have one of your VMs be your OpenFlow switch. And this is what we're going to do today. So today we're going to have our hosts, the end hosts, and all our OpenFlow switches are going to be OVS switches where you can have access, you can go and see, you can see your flows, you can do TCP dump and all these things to debug your OpenFlow experiments. Now, for those of you that took the intro to OpenFlow tutorial yesterday, you probably have seen these slides, but I think it's important for me to repeat it again because we see this all the time of people, running into these problems. So the first thing when you're writing your controller, and generally when you're OpenFlow enabling a network, the problem is that suddenly your controller is responsible for all the network traffic. So even if there is no application traffic in a network, the networks are never quiet. They have all this coordination protocol that goes, all the topology discovery, STP. There are many other networking protocols that runs between networking elements outside the application data, like video or email or whatever you might do at the end. Suddenly, the moment you OpenFlow enable a switch, the switch does not do anything by itself. It relies on to the controller to do everything, to generate this type of traffic and to forward and handle this traffic. So keep in mind that, you have no LLDP when you're doing that. So if you want to discover your topology, you have to do it yourself. You also have ARP packets and DHCP packets, which you don't usually think when you're writing your application, because the host, the host will just generate ARP packets, the intermediate host will just, forward them, and you don't really see the ARP packets. But unless your controller handled ARP, you won't be able to exchange any traffic in your network, right? So keep in mind, and maybe a good thing to do is, especially when you're doing software switches like OVS, you can have it as a normal learning switch, right? Before you enable really OpenFlow and point it to a controller. Start sending some traffic, take a TCP dump, and see what type of packets are there, just so that you understand what's happening in your network and what type of packets you're responsible for. Now, another problem I've seen people having with OpenFlow is when they're writing reactive controllers. Do you know what are reactive and proactive controllers? Yes? Yes? OK. So when you're writing a reactive controller, which basically means that you're waiting for the first packet to hit your controller before you install a flow, then the problem is that if you have UDP traffic, if you have TCP traffic, it's easy because there is only a SYN packet goes, whenever it gets to the other end, so it will go to your controller will install a flow, it will go to the other end, the same will happen on the way back with a SYN-ACK packet. When you have UDP type of traffic, then there is no coordination in the beginning, so basically the source will start blasting packets in your network. The first packet will hit the switch, there is no flow there because you're running a reactive controller, so it will have to go all the way to your controller to ask to install the flows. And by the time this packet goes all the way to the controller and back, basically you have thousands of other packets blasting your network all the way to the controller because they will still not have a flow. So by the time you manage to install a flow, you might have like thousands of packets coming to your controller, which probably is going to bring down your control interface between the switch and your controller, because those interfaces are not configured to handle high rate of data, right? It's for 1, 2 packets. OpenFlow was basically designed mostly for proactive controllers that go and install the flows before you see packets. So when you take this approach, be very careful about what type of traffic you're sending in your network and account for cases like UDP. Now, another problem people are having when they're trying to do OpenFlow experiments in the performance they get in hardware switches. So at least for the switches you'll find in Genie, you'll find out that not all actions are supported in hardware. So all the hardware switches in Genie are 1.0. And this was a little bit of it was the first real spec that came out. It was the first spec supported by hardware switches. It was a little bit underspecified, and it wasn't really clear what you should do when you don't support some things in hardware. So many people, switch vendors, what they decide to do is go and implement this in the software, right? So they wanted to support the full OpenFlow spec, and they said, oh, my switch does not support this in hardware, I'll just implement it in software. What happens when you implement these things in software is that you're suddenly taking the slow path of your switch, and the processors on the switches are not very powerful, right? They're not the CPUs that you will get in a general purpose computer. They have like very, very slow processing because that's not what they're designed to do. They're not designed to forward packets on the slow path, on the software path. So what you'll get is very poor performance. And if you're not careful about how you send your traffic, you might actually spike the CPU on the switch and bring the switch down, depending on how much load you're trying to pass through this software path. So before you deploy any controller in hardware switches, make sure you understand the limitation of the hardware switch you're using. Another problem that we see is that when you want to bring up an OpenFlow topology, usually it's because you want to control forwarding. If you want to control forwarding, it means that you probably have multiple paths in your topology, or there is no interesting forwarding you can do in your network. So you're probably going to have loops, right? If for people that want to do multipath research and use OpenFlow to do load balancing or any of these things, you're going to have loops. But you don't have SDP. Like there is no one that takes care. You don't have a spanning tree. There is no one to take care that broadcast traffic does not loop around, right? And I've seen this very recently with an experimenter that wanted to bring up this very complicated topology, spanning the one and everything. And then when we brought it up, there was suddenly no forwarding happening because, so it was just running a learning switch controller, and there was broadcasting everywhere. So it created a broadcast storm in the network, and nothing was being forwarded. So if you do have loops in your topology, make sure you take care of them one way or the other, either by hard coding one path for broadcast packets, or by running something like SDP in your network. so that you always, when you have broadcast, you don't just blast it in the network. Okay, and this was everything I had to say about OpenFlow. Do you have any questions before we move to the LabWiki part? No? Mike? I know it is Divya, but Divya is working on something now, so Mike has agreed to.
Yep.
Thank you.
So I have the wonderful task of speaking to slides I've not made myself, so.
Oh, no, you did make the slides.
Oh, I made the slides, but I haven't seen them in a while, so. Okay, good morning. Thanks for coming to the tutorial. Niky gave you a more general overview on OpenFlow, and I'm going to start talking a little bit about the tools. One of the tools you will learn about today is LabWiki. Actually, the guy who has invented that and thought it all next out sits in the back, so I'm feeling a little bit intimidated to speak to it right now. He's a pretty tall guy, by the way, also. So we will look at, I'll just give you a quick overview and give you some idea how to use this tool and what it was created for. And basically, we are hoping that you are using, the GENI test beds and the tools for experiments that help with your research, right? So you have a great idea. You want to, prove that idea by, running this at least in a test bed and generating some results. And so what we all know is what you do over and over again is, or what you do is running these experiments over and over again, right? And so we want to help you with making this process, this experiment cycle, a lot easier and streamline it. And so, as you've seen before, there's kind of these three major steps. You kind of design your experiment, you set it up, you execute it, and you often think a lot about the data you're collecting then, and change your design, change your setup probably, and go in another loop, and then run it over and over again. And we have this running, or this kind of long-lasting joke now, what we say, if you really get to the point where you then can publish your results, that is what we call the successful experiment cycle, right? That's where you ultimately want to go. I see a lot of people who I assume are grad students, right? We want to, or you guys want to, with your advisors, want to get your work out. So that's kind of important. So how can LabWiki help you with that? Here's a quick screenshot. I don't know if Niky has it already open on her computer, but it's an interface to your experiments you can think of, and it helps you with managing. And there are several important pieces. If you look at the left-hand side, that's basically where the wiki part comes in, right? So you can actually keep track of your experiments. I think of this as the digital version of your good old lab book, right? In the old days, people had lab books where they took notes about all the kind of things doing their daily work. And this is what you can do here, right? You can, take note of what kind of experiment topology I used. You can take off your results. You can maybe take, note of what parameters you have used to run your experiment, certain thoughts you might have about your experiments, how you want to evolve them, and all this stuff. So it keeps you kind of, hopefully helps you with keeping track of what you're doing and also organizing your thoughts about the experiment a little bit. The middle part of LabWiki, this middle pane, is actually pretty much your work zone, I would say. This is where you're editing, right? This is where you can edit your wiki part. So the left-hand side is actually all in Markdown. And then you can also edit your experiments. So what you see here, it's a little bit hard to see on this slide, is actually an experiment script that describes how a certain experiment is executed. And that has to be tailored to the topology you're using for your experiment, right? So you want to have certain nodes do certain perform certain things. You want to have certain measurements happening at certain nodes. You might want to have something like data transfer going on between nodes. You might want to execute things. That's what you define in that Then on the right-hand side is actually where you then can execute your experiment based on a topology, based on a slice you have already reserved. Niky, do you have a LabWiki open already on your? No. Okay. If you, well, let me just go through the slides. I'm sorry, and then we can maybe. So when you run an experiment on a Genie testbed, there's quite a few things going on, and we have tried to show this here on this slide a little bit, where you can see, you can picture yourself as the experimenter here, and then there are pretty much 6 important steps, right? Number 0, as good computer scientists, right? We start with 0. You reserve your slice, right? You need resources to run an experiment on. That's the first step. And then you instrument your slice and to be able to observe your experiment. And then in the second step, you run it, and in the third step, you collect the information from your experiment, right? Because you want to, keep that somewhere to store it, and then, be able to observe it, but also archive the data so you can look at the data you've created or measured in the long term, and obtain some results. And so what we like to do with LabWiki is actually automate a good chunk of that and help you, make this a little bit, streamline it. I don't know if easy is the right term, but make this a little bit more straightforward, and you don't have to touch every single part of these. That's kind of the functionality you're getting here, and with that, and you're getting a little bit of automation of that. So some of that is hidden from you, but I wanted to give you a better overview on this. I'm going to skip this because I would like to show you that LabWiki is open source. Here's the link to the code. You can send bugs if you come across something that doesn't work as you think it should work. And the cool thing with it is it's pluggable, so you can, if you think there's something important missing, an important module missing, you can actually write your own plugin. For example, we're using iRods for storage. If you have another long-term archive solution in your institution, you could write another plugin for the storage. You could write plugins to other testbeds, right? So if you're coming from another country and run testbeds, I know there's testbeds in Europe, there's testbeds in Japan, there's testbeds in Brazil. You can actually write a plugin that would also work with these. Okay, so can I have 2 more minutes just to open LabWiki? Can I ask that? Well, no, here's what I will do. Are you logged in the portal somewhere? Maybe. Well, let's try that. We'll see that in a second. Yeah, can you just log in? Sorry. You're going over via GPO credentials, right? Oh. Seems to be a little bit of traffic on the wireless network. Niky, one quick question. What is it? Command shift minus? No, command minus to? Command minus, right? Yeah, excellent. So you can actually, is that okay if people go to LabWiki already? Or does that interfere with your tutorial right now? I don't know, because Divya made multiple instances. Okay, so don't do anything, just look at me. So, sorry. So here's I opened a LabWiki session here, and so we have a couple prepared scripts here in already. So I'll show you just one we used for an old tutorial. Niky and Divya will point you to your right wiki here for your tutorial in a second. And you can see here how you have some information, right? There's some information about a tutorial, what to do, and so on. And what you can do is actually, you can, if you want to edit it, you can just pull it over here. And now you have the chance to make any modifications, right? If you have a new result, you want to take some notes, you want to write down a paragraph on that, you can make that in here. If you add something, right, you can save it and can then look at your edits over here. Might take a moment here. It seems to be with the network issue. Also, this wheel is kind of a little bit important. I'm just giving you some of the basics. Here you can create a new file. If you want to have a new wiki entry, complete new wiki entry, we can create this here. Make sure that you actually have select the wiki because that's for the wiki entries, but then the OEDL is the OMF experiment description language. Here you can actually describe your experiments with that language. So let me just go to that side and pull up a script here. So that's an experiment script here coming up now, and we can increase that window a little bit. And now you see an experiment. They'll talk about what's in this experiment description language in a minute, and you can now define your experiment, and that then gets automatically executed, as I will show you in a moment. So you can even also here you can create a completely new one. I think in the beginning you might want to use some of our examples to just get a little bit of the feel for it and get used to it. And so when you're done with that, what you can do here is actually same thing as on the other side. You now put this in your execution pane here. You get some information based on what's in that script, and now you're pretty much ready to run your experiment. Right? I don't have a slice for that special one up here, so I'm not going to run anything. There's no resources bound to it at the moment, but you will do this in a moment in your tutorial. Okay? Any questions about this? Any questions about LabWiki? So I'll be also in the room for the next hour or so. So if anything comes up, please feel free to ask. Thank you. Let me get unwired.
Okay, so now let me talk a little bit about the experiment we're going to do today. Wow, that was weird. Okay, so I mean, I'm pretty sure by now it's the third day of the conference. You've seen this many times. In our design step, we're gonna for this experiment, we're gonna do a network load balancing and OpenFlow type of experiment. So we're gonna have a topology that will have two paths, and the whole idea is to try and write an OpenFlow controller that will actually load balance your traffic between the two paths. And we have already reserved the resources for you, so to make this faster, because the point of this tutorial is not for you to go and learn how to use Genie necessarily, but how to learn to write these OpenFlow controllers. So, okay, what is a balance service? So basically, we will try to load balance between two or more service providers, right? That's any load balancer, whether it's a web server load balancer, any type of load balancer is trying to do the same thing. You have a load coming in, you need to serve it, and then you basically load balance it between different servers. So, in networks, this usually means balance your traffic between one or more paths, right? So, and this is exactly what we're going to do today. So we need the load balancer to be running at any point where we have to make a decision, right? Everything else on our network can run a normal learning switch. And we only need to do load balancing at the points in the network where we actually have choices to make. And I'm going to show exactly how your topology would look like now. So we're going to use OpenFlow, and as we said before, OpenFlow is the main thing that is responsible for populating the forwarding table on your switches, right? So your controller will be the one that will actually make the decision, do I go left, do I go right, and install the right flows and all the switches in the path. Okay, and also remember, this is just a reminder that with OpenFlow, you can get statistics from the switches about the traffic that goes through, and you can do it per port, you can do it per flow, or you can do it per table, in case you were running an OpenFlow version that has multiple tables. Okay? So keep that in mind while you're trying to write your load balancer controller, that you can actually query the switch about the current state in your network and figure out what is the load in its port for its flow while you're trying to make a decision where to send your traffic. So, as I said before, in today's experiment, we're going to have two paths from source to destination. And the task will be to try and balance the traffic between the two paths so that both paths are equally utilized. We are only going to use TCP flows, and TCP flows actually that have similar performance. So we're basically just going to test it with iPerf. We're going to start multiple iPerfs from a client to a server, and then you will try and load balance these specific flows. OK, so let me go a little bit over the topology of your experiment. So as I said, you're going to have two different paths. You will have the source on the top, the receiver. When your slice come up, this might be inside and outside, but it will be obvious from the instructions. Yes, I'll go and bring you the instructions just in a moment while Divya is doing the demo. OK, and you see we have like 4 switches in our topology. And the main places where we actually need to make decisions are the 2 places where we split paths. In order to make this simpler, what we've done is that we already have a controller here that will basically replicate whatever decision your load balancer will make on the top. So if your load balancer says right, then the other switch will say, take the right path as well for the reverse traffic. OK, so how this will work out is as we're designing, we're going to start a controller. We're going to connect the switch to the controller, and then we're going to start several TCP flows. And what we're going to do is measure the performance we're getting out of each path to see how well of a job we're doing in load balancing the traffic in our network. OK, so and which are the places that we need to monitor our experiment in order to make sure that our controller works as we expect, right? We're going to have 2 monitoring points. So Mike talked about using LabWiki to monitor different parts of your network. So we're going to monitor the traffic that is coming out of these 2 interfaces of your switch. And based on, and then we're going to plot the throughput that each path is taking. So you will see in LabWiki that we're actually plotting the instantaneous throughput. So you might have a little bit to zoom in to see exactly what's happening. But the idea is that we're going to monitor these 2 paths, get the statistics back, and then we're going to decide whether our controller is working, if we're getting the performance we're expecting. OK, so as I said, we have already reserved the resources for you. This is the topology you're going to see. And then you're going to go and execute the experiment. But before you do it, I think it's better if we go through a run-through of the whole experiment so that you understand how you start your controller, how exactly you run the specific experiment in LabWiki. Divya will do that. And then we're going to be done, and then you can go and start doing this yourselves.
that better? Okay. So this is the link to the tutorial page, and today we'll be following the steps that are given here. So as Niky explained earlier, this is the topology that we've pre-created for everyone who's registered for the tutorial. And since that is done, let's look at how we can run our experiment. So in the topology that Niky showed earlier, we have one node which is connected to the switch node, and these are the two interfaces out of which the traffic goes from the switch node. So you have an input interface and you have two output interfaces. So in order to specify where exactly we want to take the measurement to see if our load balancing is working right, we need to make a note of the two interfaces on our switch nodes. So the first step here is to log into the switch and aggregator nodes. And since this is a demo, I've already done that. So, okay. And I'm going to run these steps here. So what this does is it starts the tremor controller in the background for the aggregator node, which sort of emulates what the switch node is doing. So we are actually going to run our load balancer algorithm on the switch node. And here I just, okay, and I'm just going to make sure that the controller is started here. Yeah, this is the Fire SSH. I'll just open it up in a better terminal. Okay. This is okay. So since I started it in the other terminal, I'm just going to check if it's running, and I can see here that it is running. So the controller, the aggregator node is started now. So on the switch node, I need to run these two commands here. And what this does is it just sets the path for the Tremor run, because Tremor is a Ruby, we're using Tremor, the Ruby gem, and we just set this path. Okay, so now we're ready to start the controller on the Tremor, on the switch. And we scroll down here and copy this line, which starts the controller. And my switch should connect in a few seconds. Okay, the switch is connected. And now it's just waiting for us to send flows. And we'll do this using LabWiki. So from LabWiki, what we do is we start a server on the inside. We start the server on the inside node, and then we send flows so that we can see how the load balancer is working. And we use a trace application to monitor the two interfaces where the flows will be going out from. So now I'm going to open a LabWiki terminal, LabWiki in my browser and run this experiment. So as you can see, it asks you to log in using your Genie OpenID. So I have a script here that says loadbal.oedl. So this is a script which is available on Appendix A here. And let me just go through the script a little bit because it's a little long. So we say that the sender is the outside. Oh, sorry. Is that better? Okay. Yes, so the sender is the outside node, and the receiver is the inside node. So we start up the server on the receiver node, and then we start sending the IPerf from the sender node, which is outside. And we are going to measure the interfaces of the switch node. So this just defines those as the properties for our experiment. And left and right are the two interface addresses. This is what we will obtain by doing an ifconfig on switch. I'm going to stop the controller for a moment so that we can do that. And here, I can see that my Ethernet 1 is mapped to 2.1, and ETH2 is mapped to 3.1. So these are the two interfaces where I want to measure the flows going out. So I'm going to take ETH1 and ETH2 and leave ETH3 out, because here I'm not interested in measuring what flows are coming into my switch node. So if you're not able to see the script in LabWiki, what you have to do is copy the script in Appendix A and just paste it into your LabWiki window. Since I already have it, I'll just run it directly from there. So we have to define certain properties, and these properties would be variable. We would want to change them if we are running them with different topologies or running them with other experiments. So we would want to define them as properties and not hard code them. And in a moment, I'll show you why this is defined as a property here, is so that we can change it here, and you don't have to go back into the code and change it if you're using a different slice. So that is the first part of the script. And here we are going to do the measurement of the TCP packets in trace, and we are also sending the flows using IPerf. So we define the two applications, TCP, and we define the two applications here, which is trace and IPerf. So here we specify the binary path of IPerf and trace. This is because, unlike in the tutorial yesterday, we are not writing our own application here. We are using an application that's already provided to us. So this application is already installed in the images, which we've created your R specs with. So we don't need to go back and log into the nodes and check the path, and we know that this is where it's going to be. And it's the same with the trace application. So this is just defining the properties. If you compare this to the regular IPerf commands or in the case of trace, the TCP dumps that you run, you will see that many of the commands that you see here are very similar to what you would use on the command line to do your measurements. So this here, what it does is it starts the iPerf server. And when I say def group, I can have more than one node in the def group. So if I want to start more servers and clients, I have to just add a comma here and just type in the property name of the other node where I want to start the server. So my first step would be to define the group where I want to start my server, and then I define the group where I want to start the client. And after that, we go to the monitoring part, because this is also what we are really interested in, because this tells us exactly how our load balancer is performing. So we monitor the two interfaces. We monitor the left interface and the right interface, and this is done using the trace application. So at this point, we're actually running the experiment. So it matters what order we give these commands, in the sense that we need to have our server running before we start sending flows. So that's why we have the server group that's starting its applications first, and after that we have the client which sends the flows, and then we start the monitoring. And this here is the graph, which is, I guess, what we are really, really interested in. So we go to the, here what we are measuring is the throughput out of the two interfaces, and this will tell us exactly how our load balancer is working. In fact, in the graph, when you use the different load balancers that are already preloaded onto the VMs, you will be able to see that you see different graphs for both based on what algorithm the particular controller is using. So I'm going to go here and select the project. And the slice that I've already created is create exo image. So I'm just going to replace that here. Yes, so I believe those were the right interfaces of my switch node, and now I will start the experiment. So I'm just going to leave that running in the site so that we know when the iPerfs are started, that you'll be able to see what your flow statistics return from the switch node when you run the controller here. So we'll just wait for a few minutes while the experiment starts. So the pending status says that your job is still being scheduled in LabWiki. So we wait until it goes to running, and that's when we know that the application has started. So if you want to check the status, OK, I can see that it's running. But if you want to check the status of your experiment, you can just type the experiment name that you see here into this search panel here. And you'll be able to see what the status is. It's taking a few minutes here to start the flows. So in this script pane, you can see a name of the URL here, and this is where you can actually go to get the logs of your experiment and see why it's taking so long or why it's not running. It could possibly be because of some problem on the client side. So when you visit this URL here, you can see that there's a log file link. You can just copy that into the browser. And we can see the logs here and see why our experiment is taking so long or not running, or maybe we just need to wait for a while. So now I can see that it says there is no route to host, which means there might be a problem with my controller, or the previous message here says that the address is already in use. So it is possible that in my previous run of iPerf, I did not remember to stop the iPerf server. So it says it cannot connect, or it cannot find the route to the host. So I have to log into my nodes and now see exactly what is going on. Here I can see that there's one server running. So we can leave that and go to the client and see what's going on there. Let me see if my controller is running fine. I can see that my controller is running here. And on the switch, it's running too. Okay, I see the client started as well. So let me just go back and restart this. Do we want to start the hands-on? Yeah. Before.
It's getting closer. I think it's better if you get, a hands-on experience, and then if you want, we can do another demo at the end. So basically, I gave you the instructions. You should probably be the online version too. So if you go to the GEC19 agenda and you go to the session page for the advanced OpenFlow, you will find the link to the instructions there. So you have also the online version. So basically, you will start from the portal, and you're only set, so you should have an account in the resources. So basically, go log in the portal. Find there will be a slice called OFLB and a number, and that will be your slice. Go to the details in exogeny SM. So there's exosem. So you will find. Let me actually, Divya, can you bring the portal?
The portal?
I can show you exactly instead of just talking to it. Okay, so you log into the portal like you would usually do. Okay. And then if you go to your slices, in the second where it says slices on which I'm not the lead, you will find, and Divya has too many slides, the slices. Yeah. Okay. You will find, no more. Okay, you will find, you will only have one slice. You will find a slice that says OFLB, and you will choose that slice. You will load it. And then you will go here that says ExoGenie ExoSM. Victor, is it okay if we all press to try and get the manifest at the same time? If we all try to get the manifest on ExoSM at the same time? Okay. So then you go here that says details, you press, and this should bring up all the login information of your nodes. And you should all have an account there. If someone does not have an account, let me know. We created the slices after you added them. So if you don't have an account there, we also gave you a common key that you can use. So if you don't have an account, if when it loads up you don't, oh, sorry, I choose a slice that has no resources. But if you, let me actually choose one that has resources. So if you go through all this SSH information, there are going to be many of them because there are many admins in this project, but somewhere you will find your own user ID. If you don't find it, then call me, and we can log in using the common key you downloaded in the beginning of the tutorial. So you should get something like this, and if you scroll here, one of these should be your own username. Okay? So, and then you just click and you open up the SSH. Let us know if you have any problems.